Good evening, everyone. My name is Dustin Bracey, and I'd like to make a little presentation on deep pruning, or methods for deep neural network optimization. So what we're going to cover tonight, we're going to talk about what is a neural network and why they need pruning, what is pruning, how is it different from dropout, and then we're going to do a deep dive on pruning methods, and then we'll get into our takeaways. So, neural networks, a brief overview before we get started. A basic neural network is comprised of a lot of perceptrons and multi-layer perceptrons, which I'm going to get into in the next slide here. But in the basics here, we have at least 3 layers. We have an input layer, one or more hidden layers, and an output layer, which comprise our neural network. So our input layer is just a vector of features. That layer doesn't really do much. It just passes the input values into the hidden layers. It doesn't apply any weights or operations. That all happens in the hidden layer, and that's where our magic happens in the neural network. So the hidden layers invoke some activation function and apply weights to inputs, and they direct that weighted output to additional hidden layers or to the output layer. The hidden layers are typically fully connected or dense, which you can see here. The X1 feature is connected to all 3 nodes in the hidden layer. If we had more hidden layers, each node in the first hidden layer would be connected to every node in the second hidden layer, so on and so forth. And then that output layer receives the output from the last hidden layer and ultimately makes our prediction from the model. So let's get into it a little bit here. So multi-layer perceptrons. A single perceptron is defined as follows. The output y is the product of some activation function phi, and it's going to look at a vector of inputs. It's going to take a vector of inputs. Each input has its own weight vector. So you are taking each input, multiplying it by a weight, and then adding some bias term, which is our beta there. And then it goes through the activation function and ultimately ends in our output. So if we look at something like linear or logistic regression, we can think of our features as features, right? The weights as coefficients, the beta or bias term is our intercept, and then it's going to go through some sigmoid function in the case of logistic regression to give us an output between 0 and 1. Multi-layer perceptron takes that a step further, and then we can take our same input vector, we're going to get an output vector x and an input vector s. We're going to apply some function that I'm going to go through here, inside out. So we have our capital A is a matrix of weights of the first layer. S is our inputs. Again, we're going to add our bias vector or bias term for the first layer, and then we're going to go to the outside. The capital B and the small b are the weight matrix and the bias vector for the second layer, respectively, and those are going to go multiply against our activation function. And so the activation function is a parameter we can tune. We can use something like sigmoid, like logistic regression, or a hyperbolic tangent, which is similar to a sigmoid, but it can go from -1 to 1 instead of just 0 to 1. We also have more exotic things like ReLU and LU and those sort of things. But let's get into the pruning. What is pruning, why it matters, and the whole point of this presentation here. So, pruning is a deliberate reduction in features and or weights per layer. We have a couple different methods that we can use to prune. We can prune the synapses, or the weights, that sets the weight to 0, and it effectively removes the feature interaction. Just like stats, when you multiply 2 features together or coefficients, you get that interaction term. Pruning the weight removes that interaction term, whereas pruning the neuron or the node or the unit, it removes the entire column vector, removes the node, all of the weights associated with it, sets the whole thing to 0, and that feature is deleted from the model. Now, so this is a pretty simple example, but you can already see that large networks have an extraordinary amount of data and interconnected features. This naturally kind of results in a lot of redundant features that may not be needed for our problem space, if we're using something like transfer learning in a convolutional neural network. So in that example, if we have a huge network model that we're starting with, like ResNet, it's trained on millions of images over thousands of categories, but we only want to predict dog breeds, there's a lot of unneeded information and connections that probably don't matter for the hundreds of other categories besides dog breeds. My model may not need to know the edges which define the difference between a bus and a car, for instance, to correctly label a beagle. So, why introduce pruning? We talked a little bit about that there, but there's three kind of key points here: efficiency, speed, and accessibility. So efficiency reduces the size, it tries to minimize performance impact. Smaller models offer faster training and inference, and accessibility, compressed models can be deployed to limited resource environments. What does that mean? Mobile phones, Raspberry Pis, the Internet of Things, domains that deep learning has never existed before. We can really push this inference and this transfer learning down to fields that had no access to this before. That's really exciting. So let's talk a little bit about the difference in pruning and dropout. So dropout is kind of the foundation. It's pretty much widely used in deep learning right now, and it randomly drops nodes, and it occurs during training. Pruning is a little bit different, where it selectively drops nodes and occurs typically after training. So some of the theory behind dropout is it's usually used as a method of regularization. It's kind of frequently implemented to help control overfitting. So the ideal model of training a neural network would involve running every permutation of parameters and averaging the result. Now, obviously, that would be extremely computationally expensive and inefficient. Dropout tries to emulate that efficiently by randomly dropping nodes from each layer, breaking all of those connections, and effectively changing the layer shape. Now, because the neural networks tend to build highly accurate, complex co-adaptations that don't necessarily generalize well to new data sets, implementing dropout breaks those relationships up and forces those layers to adapt new connections that generalize much better. So that's great for reducing overfitting, but as a general rule of thumb in practice right now, the ideal dropout ratio is anywhere from 20 to 50% of network nodes in the network. And the way to mitigate your network being damaged or performance being impacted, generally people are increasing the size or the width of their network. So if I have 200 neurons, I may increase that to 300 neurons and then implement a 50% dropout or a 30% dropout to get me back to that normal size, but introduce some randomness and some noise to help prevent overfitting. So that doesn't really help reduce the size of our model, it just really helps generalization performance, and we still end up with kind of a really large, really complex model. So if we look at something like an iterative pruning approach, which is we'll get to when we talk about targeted dropout, we go through this process, we fit the model, we evaluate importance, we measure the effect of those nodes and the weights to select the lowest performers, we drop those low performers, we evaluate impact, and if the loss, the increase in loss or the decrease in our AUC is acceptable, then we continue, and we continue this pruning until it's no longer acceptable, and then we stop and we move on. So let's do a deep dive here into methods. I'm going to talk about three methods primarily. There's a lot out there, but I'm only going to get to three, and really it's only two. I'm going to talk about traditional because it's not really a method to prune. It's more of just like I said, a regularization method, but because targeted dropout really depends on it, I want to touch on it. So, traditional method uses a Bernoulli distribution, which is just a probability distribution of drawing a binary number. So, a Bernoulli mask then is a drawing of a random binary number for each input. So your vector of inputs is going to be multiplied against this mask vector of zeros and ones, and that then is going to be multiplied across your weights. So for unit dropout, you have an element-wise product of tensor input x and your Bernoulli mask m, and that gets further multiplied by your weight matrix. And weight dropout is the same, just in a different order, right? Element-wise product of the weight matrix and Bernoulli mass to drop weights then gets multiplied by your tensor input. All right, so pros and cons of the traditional method. It's fast, it's simple. Bernoulli mass are extremely computationally efficient because you're just multiplying things by ones and zeros. Your randomly keeping method is simple to use and easy to explain, easy to implement. However, you get this unoptimized output. You get the redundant and or the unimportant features remain for inference, and you get random drops that we could argue potentially we drop highly important nodes and those fall off from our model. We could argue the random forest concept that if it's truly important, it's probably going to come up again. It might be in another node, and so the randomly drop would actually help by dropping those outliers where it's really important in this one-off use case, but it's going to introduce bias later. So could be a con. All right, let's get into the Fisher pruning method. So there's a lot of scary math here, and I'm not I'm not an expert in the math, but I'm gonna try to walk us through it here. So you start with a network parameter. The goal here is to remove feature maps or parameters that don't contribute to the overall performance of the model, i.e. they don't matter for our problem set. Remember, the first formula is a general case representation of a network with parameters theta, trained to minimize cross entropy loss for outputs z given our inputs I, with the expectation taken in some data distribution p. Okay. The second formula looks at pruning a single parameter theta sub k, and it looks at for any change in parameter d, we can approximate the change in loss with a second order approximation of the current parameter value theta. Now, the last formula measures the approximate increase in loss caused by dropping the kth parameter. We're setting that theta sub k equal to 0. All right, let's keep going. So this first formula gives us an approximation of the Hessian diagonal and assumes that the two probability distributions are close. Okay, if they're equal, the Hessian reduces to the Fisher information matrix, and approximation becomes exact. That's a happy path, and we can move on. So the gradient that we use here is the pruning signal that we're going to use to greedily remove parameters one by one with the least estimated increase in loss. So we're going to use n data points using that gradient, and the gradients of the parameters at the n data point. So the second formula is the gradient for parameters that we're going to apply for weights, right? And the bottom two formulas give us the pruning signal for entire feature maps, which is what we're going to use in something like a convolutional neural network. It uses a binary mask, again those Bernoulli masks, to modify activation functions. You can see there the alpha sub a and k I j. So those masks are going to get applied to the activation function, and it's going to drop those. It's going to drop those the nodes. Sorry. All right, so let's look at how it performs. This slide is a bit of an eye chart, but it shows us a lot of really cool information. So at the top left, we can start at the methods here. LeCun in the original reference here has got a 0.8% error rate and obviously 100% computational cost. The Fisher methods here, there's three kind of Fisher methods they implement in the paper. The beta equals 0 is the automatic choosing of the weight that we looked at in the formulas in the last slide. It tries to optimize the trade-off between performance and computational cost. Beta star works by ignoring computational costs and trying to aggressively prune. And then beta greater than 0 is using fixed weights but with an optimized weight found through optimization methods after the fact. In the bottom left, we're looking at the AUC versus the gigaflops, or the floating point operations per second. That gives us an idea of how our accuracy compares to the computational complexity. Obviously, more gigaflops required to go through one cycle is more complex, and we're looking at a major reduction. And the far right, you can see the dense gaze and fast gaze are two pruned networks based on the deep gaze 2 method that Twitter is using for object detection. You can see the prediction speed in milliseconds there is about 3.6 or 7 seconds for deep gaze 2, and looks like in some cases are right around 100 milliseconds for the fast gaze, which is incredible. I mean, we're taking from almost 4 seconds down to 0.1 second in prediction speed, which is great for user experience. If you're using this on a phone, this is just incredible. So pros and cons of the Fisher method: it's fast, drastically reduces model complexity for inference use cases. It's simple, it's relatively easy to use despite all the math, right? It only requires a gradient. Once you figure out how the gradient works and you can apply it, it's really pretty simple to implement. It's optimized. The weights are, they're already weighing computational complexity against performance. However, it can be costly, and parameter tuning may be infeasible on expensive models to come up with that optimal gradient that we saw in the charts. So let's move on to targeted dropout. This is implemented by the folks at 4AI in Google Brain, and it looks at improving the dropout that we already use in everyday deep learning models. So it uses stochasticity and magnitude-based pruning. So it takes the top k elements and it says these are the most important, and uses an argmax k to return the top k elements out of all elements considered. What does that mean? It drops the lowest performers, basically. So you have the expected units to keep for each round is 1 minus gamma times your activation, your probability value. So you have a targeting proportion with a drop, which is your gamma, with a drop probability value alpha, and that accounts for low value elements which may become important later, i.e. we're dropping a lot of stuff that is not important now, but after we drop 30% of our nodes, it would have become important later. So considerations are made there. The unit pruning and the weight pruning look a lot like the Bernoulli masks that we saw earlier. They consider the unit column vectors of weight matrices under the L2 norm for unit pruning, and for weight pruning it considers each entry of the weight matrix separately under the L1 norm, and then again applies that kind of matrix multiplication to multiply element-wise for all of your weights or nodes. So okay, great. Let's talk about performance. So I highlighted a couple columns here for you. On the top you see weight dropout performance, and the bottom you see units. On the left you can see no action taken with just basic dropout applied from 0 to 100% prune or 99% prune. And then the targeted, the 50% column I have highlighted there, you can see for weights, if we get into 50% targeted prune on weights, the accuracy performance is actually higher than anything that we did in just the plain Jane dropout, 94.33, and that's with 50% of the weights removed. Now the node, pruning the nodes themselves, obviously you can see a giant performance impact there if we do nothing. However, dropping 30% of the nodes, doing nothing, goes from a 94% accuracy to a 36% accuracy. But when we use targeted drop and an L1 regularization, we're still at a 91.97%. We got like a 2.5% drop in accuracy, and we're deleting a third of our model. That's incredible. So pros to targeted dropout, only pros, right? It's intuitive. It works like feature selection in a traditional machine learning. You select the most important, the most bang for your buck, and you keep those nodes or you keep those weights. It's simple. Dropout is already widely used. This just adds a step. In fact, the researchers provided a Git repository on GitHub that gives you a drop-in replacement for your normal dropout. You can drop into TensorFlow or PyTorch. It's awesome. It's optimized, it drops unimportant features, it minimizes size and complexity, and it's incorporated. All of that pruning occurs during training, so you don't have to go spend weeks training your model and then more weeks pruning it later to increase your inference speed and increase performance. So, takeaways. Finally, right, we're here. Methods reviewed. We looked at traditional methods, which is no pruning, and it results in large models. We're just applying dropout. Fisher pruning, which is after the fact pruning, it speeds up inference. Targeted dropout prunes the least important nodes to reduce size. Now, this kind of brings it all together. So if we look at the Fisher pruning chart on the left here, we've got AUC versus gigaflops. You can see deep gaze 88% AUC compared to fast gaze at 85%. We take a 3% hit, but we're going from 240 gigaflops to just 10 at each iteration, which is crazy. Fast gaze detects objects 39 times faster than deep gaze. We're going from almost 4 seconds to 0.1 second, and that is giant for user satisfaction, right? 50% of the weights were pruned using targeted dropout with no loss in accuracy. And in fact, we had an increase in accuracy in the particular, I think it was the MNIST data set in that paper. So in conclusion, pruning is a highly effective way to increase inference speed, reduce model size and complexity. That smaller size and complexity is going to reduce computational expense, which in turn is going to save time and money with a minimal loss in accuracy. With more research in this field, I think this could be really promising and a definite must-have in deep learning. These are my references, and thank you for your time. Have a good night.